Welcome back. This is unit 5.1. We're starting a new unit, and this 5.1 is on Lewis structures, and this can be found in chapter 7 and 8 of your textbook. All right, so starting a new unit. In this unit, we're going to be talking about what's called Lewis structures, where it gives us a visual of the valence electrons that are around atoms and molecules. We're going to talk about the different types of bonding that there are. We're going to actually start learning how to name compounds. And then finally, in the last section, we're going to talk about molecular shapes, the different shapes of molecules, because that helps us out when we look at how molecules fit together to form chemical equations. All right, so Lewis structures. Remember now, we've been talking about how valence electrons are the reason for bonding between atoms. Lewis structures gives us a visual of that, so we're going to learn how to draw those. And in 1916, American chemist, we don't see that very often, American chemist, Gilbert Lewis developed this system, so therefore you get to call it the Lewis structures. All right, so there's two things that you need to know for a Lewis structure, and that is the symbol for the element or the formula and the number of valence electrons for the elements. So we're going to review here. If you recall, we talked about the valence electrons being the outer S and P electrons. And so we saw that on the periodic table, there's a pattern. Let me pull over a periodic table here. We saw that in group 1, all of these have one valence electron. In group 2, they have two valence electrons. And we're going to skip 3 through 12, okay, because these transition metals do weird, wonky things. Go over to group 13. Group 13 has 3 valence electrons. 14 has 4. 15 has 5. 16 has 6. 17 has 7. And then 18 has 8 valence electrons. And when we look at the electron configuration, so clicked right up here at the top, and it brings up a diagram, and over here also the expanded and the short form of the electron configuration. Let's look at bromine. All right, so bromine, let's do the expanded first. The outer shell, the highest energy level, bromine is on the 4th principal energy level. So we're only going to be looking at the S and P electrons that are in this 4th level. So here in the expanded, we have 4s2. Now we don't count the 3d10 because those are lower energy electrons. We're only counting the highest principal energy level, which is 4. So that's 4s2. Then we're going to skip over here to 4p5. So here, 4s2, we have these 2 electrons. We're going to skip these. And then we have 4p, 1, 2, 3, 4, 5. It's in the 5th position. So we have these 2 and these 5 that make up 7, the 7 valence electrons. And over here in the diagram, we see that as well. So here's S and P. We have 2 in the S, and then we have 5 arrows here in the P. So 5 and 2 is 7. So when you're looking at this, let me leave this here. So when you're looking at this diagram here, so bromine is in group 17, you see this NS2, that N is just substituting because we don't know what principal energy level that you would be talking about for a particular element. So here, since we're talking about bromine, we can substitute 4 for this N. So 4s2, 4p5. Okay, so 5 and 2, 7. So that's what that symbol means. The N, you just substitute for whatever principal energy level that element happens to be sitting on. Okay? All right. So Lewis structures for individual atoms. Okay, so here are the steps for writing a Lewis structure. You write the symbol. So let's say we're going to stick with bromine. So we're going to write the symbol. Okay, represent the valence electrons as dots that are placed around the symbol in the north, south, east, and west side of the symbol. So top, bottom, left, and right. So valence electrons. Okay, so here we have 7 valence electrons. Okay, the third thing to remember is that if you have more than 4 valence electrons that you're representing, you're going to first fill in the 4 compass points, north, south, east, west, and then you're going to go back and put a second dot in those quadrants until you have 7. Okay, so we're going to do 1, 2, 3, 4, and then 5, 6, 7. So this is what bromine looks like. Okay, this is the Lewis structure for bromine. So if we look over here at this table, this shows us the elements from hydrogen to argon. So here we have 1. Here we have 2. And then we start over on a new period. Lithium, 1. Beryllium, 2. Boron, 3. Carbon, 4. 5. 6. 7. And then finally neon, 8. So you'll see that the most dots that you're ever going to have, since this represents valence electrons, the most dots that you'll ever have are going to be 8, because there's no element that has more than 8 valence electrons. And you'll see that the most you'll have on any given side is 2. Okay. All right. That's Lewis structures for individual atoms. Now, we know that atoms do gain or lose electrons. Since we're talking about electrons, we need to take into account for that. And when atoms gain or lose electrons, that's called an ion. We've talked about this before. So how would you use the Lewis structure to represent ions? Well, let's take hydrogen, for example. Normally, hydrogen has this 1 valence electrons. Now, I want y'all to write this down. Metals give away electrons or lose electrons. Nonmetals gain electrons. Okay, so just as a reminder, let's look at metals and nonmetals. So remember, metals and nonmetals, metals start here at boron, okay, and it stair steps down just like this. Let's go back to the regular periodic table so you can see this. So here it's stair stepping down, and you see along this line those light green metalloids. Okay, remember, metalloids touch this stair step line. So it starts here and it goes down and it just stair steps. Right? Everything on the left here, right. I need to know my directions. Everything on the right here is a nonmetal. And then everything here on the left is a metal. Okay, so if I look just at the metals, everything there on the left is a metal, and everything on the right is a nonmetal. So these donate their electrons, give away electrons, lose electrons. These gain electrons. Okay? And I know we've talked about that before. Metals give away electrons, nonmetals gain those electrons. So hydrogen is really not a metal or a nonmetal, but it's on the metal side. So hydrogen usually will give up its electron. So it's going to give this electron away. So we're going to rewrite the symbol. And now it lost that electron, so it gives away this negative charge. So now hydrogen's going to be a plus like this. So how do we represent that? Well, we draw the symbol, and then we put a bracket around it. It doesn't have any electrons there, but it does have a positive charge, so we just draw a plus sign like this. Okay, now let's look at, this is called a cation. Remember that, a cation. It's positive. Cats have positive. So that's how you remember a cation. Now let's look at the other one. The other one is called an anion. Anion. All right, so chlorine, okay, has 7 valence electrons, so we're going to draw 7 dots here. Okay. It usually gains electrons, so it only has one spot to gain an electron, so it's going to gain this electron. Okay. And so chlorine has a -1 charge. So how do we draw that? How do we represent that as a Lewis structure? Well, we're going to put it in brackets just like we did the hydrogen, but we're going to draw, pardon me, the 8 electrons around it that it now has. Okay, and then we're going to write a little negative sign out there, just like that. Okay, so that's how you represent ions, Lewis structures for ions. Now, ionic compounds. So when ions form compounds, they do it in a way where they're, pardon me, when ions form compounds, they do it in a way where their overall charge is neutral. Now, what do I mean by that? Well, if we take our 2 elements that we just used, hydrogen and chlorine, we saw that hydrogen gave away 1 electron, and chlorine has a spot where it can accept 1 electron. Okay, so now this hydrogen has a +1 charge, and this chlorine has a -1 charge. Okay, so remember, think about the positives and negatives, just like the ends of a magnet, north and south. If this hydrogen has a positive charge and this chlorine has a negative charge, they're going to be attracted to each other. Okay, it's called an write this down, electrostatic attraction. Okay. And they're going to stick to each other and form a bond of HCl. And like I mentioned earlier, we're going to learn how to name these, but this is hydrochloric acid. Okay, HCl is hydrochloric acid. So it's simple when you have a positive and a negative. When these are the same, these two are going to cancel out. These charges are going to cancel out, and that's going to equal 0. But what happens if they're different? Let's look at that case. Well, let's look at if we had calcium. Okay, so calcium is in group 2, so that it has 2 valence electrons. So what's going to happen is it's a metal, so it's going to lose these 2 electrons. When it loses these 2 electrons, it's going to become a +2 charge. Okay, now let's use fluorine as an example. Fluorine has 7 valence electrons. Fluorine has a spot where it can add a valence electron. So what happens is this valence electron will come over here and take this spot. So if it's only calcium and fluorine that we're talking about, we have to add another fluorine. Okay, so that this electron can come and take this spot. And in some of your tests or some of your homework, it may tell you to represent the electron transfer between calcium and fluorine. And this is exactly what I'm doing here. This is what I'm drawing. I'm representing the electron transfer. All right, and so we had to have 2 fluorines in order to take these 2 electrons right here. So the formula for this ionic compound is going to be Ca. We had to have 1 calcium, and then we had to have 2 fluorines. And remember, when we were counting electrons doing molar mass, these subscripts, this 2 represents how many of these fluorines are bonded to this calcium. So we have CaF2 is the formula for calcium fluoride. Now there's another way that we can do this. It's called swap and drop. So what we do is we write the symbol calcium, and we write the symbol for fluorine F. Calcium has a +2 charge, so I usually put it above like this when I'm trying to figure out what the formula is. Fluorine has a -1 charge. All right, so these don't add up to 0. So that's your first question. Do these charges add up to zero? It does not. If it doesn't add up to zero, then what we're going to do is swap these two numbers, not the charge, just the two numbers. So I'm going to rewrite it. I'm going to put a 1 here and a 2 here. So I've swapped these two numbers. Let me go ahead and write a 1. We usually don't write 1s when it's just a 1, like a negative 1. We just write the charge. But for this example, showing the numbers, I'm going to write a 1 there. All right, so we've swapped it, not the charges, just the numbers. And that's the biggest mistake students do. They swap the charges with it. It's not the charge. We're just looking at the numbers. Okay, so don't make that mistake. So we've swapped the two numbers. Now we're going to drop them, swap and drop. We're going to drop them into subscripts. So calcium, this 1 drops down to a subscript. Fluorine, this 2 drops down into a subscript. So we have 1 calcium, 2 fluorines, but we don't write 1s. So when we're all said and done with this formula, we have CaF2, which is exactly the same thing we have here. Okay? All right, so one more example of swap and drop. This is probably going to be the hardest one you'll ever do. Okay? And let's take magnesium again. And this time, let's use phosphorus. All right, so let's look at the periodic table really quick. Okay, so magnesium here is going to be a +2. Phosphorus here is going to have 5 valence electrons. So it's going to need 3 valence electrons. That gives it a charge of a -3 when it takes those. Okay, so if we're looking at charges, we have magnesium, which has 2 valence electrons. Okay, and then phosphorus has 5 valence electrons. So these two are going to come, one's going to sit here, and then this one is going to sit here. Well, now 1, 2, 3, 4, 5, 6, 7. There's only 7, so we need to add another magnesium with 2 valence electrons because this needs to come here to make 8. Well, now we have an extra valence electron here. So I need to draw another phosphorus. 1, 2, 3, 4, 5. This one's going to come here. But phosphorus, we need another one. So I'm going to have to draw another magnesium, 2 valence electrons. This can come here, and this can come here. All right, so now we have filled up. Magnesium has lost all of it, and these phosphoruses have gained all of those electrons. So we know here that we're going to need 3 magnesiums and 2 phosphorus. Now let's look at that for swap and draw. So magnesium, oops, that was a wonky looking, M, magnesium. Okay, magnesium and phosphorus. All right, so the charge of magnesium is a +2 because it's in that second column. It has 2 valence electrons. It's a metal. So it gave away these 2. Phosphorus is in group 15, so it has 5 valence electrons. So it's going to gain 3, -3 charge. Okay, so you see these do not add up to 0. So we're going to swap and drop. So magnesium, phosphorus. We're going to swap these numbers. So this 3 comes over here. This 2 comes over here. We're going to drop that. So magnesium 3, phosphorus 2. Okay, and if we look at this, this is exactly the same formula we got when we represented the transferring of these electrons. Okay. All right, so this right here is going to be the hardest one you're going to do, where this one's a 2 and this one's a 3. You swap them, drop them, no big deal. It works every single time. Okay, so how do we represent this as a Lewis structure? Well, let me clear this and let's use a simpler one. Okay, so let's use the calcium chloride that we did. Okay, so if you think back, calcium chloride, CaCl2. So since calcium gave away its electrons, it's going to have a positive 2 charge. Okay, so positive 2. So we're going to draw this like this. It has a positive 2 charge. Okay, and then we have 2 chlorines. 2 chlorines. Remember, chlorine had 7 valence electrons. Okay, so it gained this 1 electron here. So that made chlorine, its Lewis structure, look like this. But we have 2 of these. So I'm going to put 1 on this side. Okay. Like this. You don't want to put 2 negatives together. Okay, because negative, they don't attract each other. So where could I put this other chlorine, negative to positive? Well, it's either going to be here, here, or here. Okay, and people like to see things symmetrical. So you're most of the time going to see it over here on this side like this. Okay, so there you go. That's calcium chloride represented, the ionic structure for calcium chloride. 1 calcium, 2 chlorines. Chlorine negative charge, calcium plus 2, chlorine negative charge. All right, so how do we represent Lewis structures for covalent molecules? Well, if you look at the book, there's going to be like 10 steps. Make sure you check, or, write the Lewis structures for this element, write the Lewis structures for that element, move electrons. That's very complicated. I never use that. You're going to see it in the books written that way and the steps on how to do it. But I have a much easier way to figure this out. And I learned this from my chemistry teacher back when I was in high school. And I'm passing the knowledge forward on to you guys. You're not going to see books talk about this. I don't know why, but you won't see this I've never seen this method in a textbook, but it works. So I'm going to teach it to you because it's much easier. Okay, and it's called nozzle, N-A-S-S-L, nozzle. So what you're going to do is you're going to write a right angle like this. You're going to put nozzle on this side, and then you're going to put the compound that you're looking for, its structure, on top here. Okay, so let's do carbon dioxide first. Now, these letters represent the steps that you're going to do to get this structure. N stands for needed. Needed valence electrons, so that each one of these elements has a full 8 electrons. Remember, we talk about having 8 electrons is what every element wants to have. So every single element on the periodic table, with the exception of hydrogen, wants to have 8 electrons. Remember 8, that magic number that we've been talking about. Now, the only reason hydrogen doesn't is because hydrogen only has this one principal energy level, this one shell. And on this first shell, the most electrons that shell can hold is 2. Okay, 2 electrons. So hydrogen and helium are the only 2 elements that have just this one shell, and that one shell needs 2. So for every single element that you're going to talk about, it's needed is going to be that magic number 8, except for hydrogen. Now, we don't have to worry about helium because helium is a noble gas and it already has 2 electrons in that shell, so it doesn't bond with anything. So you just have to remember hydrogen. Hydrogen's the only one that you're going to have to remember. Hydrogen needs 2. Everything else needs 8. So here we have carbon and 2 oxygens. That's 3 elements. 3 times 8 is 24. So if every single one of these elements has the electrons it wants to fill its octet, we're going to need 24 electrons. Well, we know that's not true. So A stands for actual number of electrons that these have. Well, looking at the periodic table, we see that carbon is in group 14, so it has 4 valence electrons. We see that oxygen is in group 16, so this has 6 valence electrons, but there's 2 of them. So 6 plus 6 is 12. 13, 14, 15, 16. So we actually have 16 valence electrons. Okay, so we need to subtract. S is subtract. So we're going to subtract these two to find out how many electrons are shared between these two. Oops, I didn't want to do that. Between these two elements. I'm sorry, these three elements when they form a bond. So 16 from 24 is 8. 8 electrons that are going to be shared. All right, so when we have two elements that share an electron, so let's write the Lewis structure for carbon, okay? And let's write the Lewis structure for oxygen. Oxygen has 6 valence electrons. Okay, 1, 2, 3, 4, 5, 6. I'm just going to draw it like this. Well, this oxygen needs 2 more valence electrons to have a full octet. And so these are going to share valence electrons. So what's going to happen is, let me get at this eraser, and let me take 2 of these valence electrons and move them over to this side. So these 2 valence electrons are going to switch positions and come over here. And it's going to share these 2 valence electrons right here. And I'm drawing another dot here, but I'm putting a line. It's going to share these 2 with oxygen. So the way we represent sharing is we draw lines like this. So when carbon and oxygen bond, it's going to form with a double bond here. This is what's called a bond. Okay. And when there's one line, it's called a single bond. When there's 2 lines, it's called a double bond. Oops, that's a B. Double bond. And 3 lines would be a triple bond. And we're going to see those in just a minute, or in the future. And a triple bond is the most that you're going to see. So single, double, or triple. So we represent these bonding areas with a line right here. Okay. Now, it could be just 2 dots. Sometimes you're going to see it. It's going to look like this. Okay, where we have oxygen has 4 left because these 2, I'm sorry, no, it's going to have 6. And this carbon's going to have 2 left. So sometimes you're going to see it with dots like this, but more often than not, it's not going to be represented with dots. Okay, at least when we draw them. So a bond between elements is 2 electrons. So when we draw a bond, this represents 2 electrons. So in order to get this, where's my eraser? In order to get this drawn like we want, then when we subtract these first 2 here, we're going to divide it by 2. Because this is going to tell us the number of bonds. Since 2 electrons are in a bond, let me rewrite this. So since this bond represents 2 electrons, we're going to divide this number that they're going to share by 2. And that's going to tell us how many bonds. So here we have 4 bonds for this compound, this molecule. All right, this next S means subtract again. So we're going to subtract these 2 numbers. So 16 minus 8 is 8. This L means lone electrons, lone unbonded electrons. So those are dots. Okay. We represent lone electrons as dots. So here we have a formula for drawing this compound. We have 4 bonds and 8 electrons. All right, so let's draw this. So we have carbon and 2 oxygen. So normally these molecules have what's called a central molecule, a molecule that's in the center. So you have to decide what's going to go in the center. Now, carbon always goes in the center. Okay, so carbon in this one's going to be in the center. If you don't have carbon, it's usually the one that you have the least of. Like here we have the least of carbon. We only have one carbon and two oxygens. Okay, so it fits that rule again. And if that rule doesn't, if you can't decide from that, then you're going to have to look at the one that's least electronegative. It's going to go in the center, least electronegative. We talked about periodic trends and electronegativity. We saw the trend. So it's the least electronegative, except for hydrogen. Hydrogen never goes in the center. So I'll keep re-stressing that as we draw these and work on examples. So we have the least amount, carbon. Carbon always goes in the center. So we have carbon in the center. Now we're going to distribute what's left over around this carbon in a symmetrical way. So we have two oxygens. So we need to do this symmetrically. So let's say I'm going to add one here. And if it's symmetrical, then I'm going to have to add the other one here. Okay. Or you could have added top and bottom. You could have added this quadrant corner, any way you want it. Just make sure it's symmetrical. All right. So here we have our elements. Now we need 4 bonds. So we're going to start off distributing these equally around these between the oxygen and the carbon. So here we have 1, 2, but we had to have 4. So let's go back 3 and 4. So there's our 4 bonds that we've distributed equally around this. Okay, so we have 8 dots, 8 lone electrons that we need to put. Okay, and electrons travel in pairs. So we're going to put 2 dots together. So 8 electrons, that means 4 pairs. So we have 4 pairs of electrons. Now the way we want to do this, remember, our whole objective is so that these elements think they have 8 electrons. Okay, that's our whole objective. So if we look at carbon here, we're going to always start with the central one and count 8 electrons. So if carbon looks out this direction, it's going to see these 2 electrons in this bond and these 2 electrons in this bond. So that's 2, 4. And if carbon were to look out in this direction, it would see 2 here and 2 here. So that's 6, 8. So 2, 4, 6, 8. Carbon thinks it has 8 electrons. So carbon is fine. We don't need to add any more electrons to carbon. So if we take this oxygen only sees this bond and this bond. So that's 2, 4. So here we have to add dots. 5, 6, 7, 8. Okay, so now this oxygen is fine. It has 8 electrons. So this oxygen needs to see 8 electrons. 2, 4, 5, 6, 7, 8. This oxygen now has 8. Now let's go back and check to make sure that we have used everything that our formula told us we needed to. Our nozzle. 4 bonds, 1, 2, 3, 4. 8 electrons, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that is the Lewis structure for a covalent molecule. Okay, covalent molecule. So let's define an ionic compound and a covalent molecule. Okay, so make sure you're writing this down. An ionic compound is between a metal plus a nonmetal. So if you're looking at the periodic table, let me drag the periodic table back over here. Okay, an ionic compound is any metal, any of those that you see that are in color, bonded with any nonmetal, any of these on the right-hand side that you see that are in color. Okay, metal plus a nonmetal. So we were bonding in our first example, calcium chloride. So here we have calcium, which is a metal, chlorine, which is a nonmetal. Okay, so that's an ionic compound, metal plus a nonmetal. Okay, pull this back over. So a covalent molecule is going to be two nonmetals. Or, let me rewrite this. A nonmetal plus a nonmetal. Okay, nonmetal plus a nonmetal. So here in our example, we have CO2. So we have carbon, okay, carbon with oxygen. So those are two nonmetals. That's going to be a covalent molecule. Okay, so this is how we decide if we're going to use the nozzle method or if we're going to use this method. Okay, if it's an ionic compound, metal plus a nonmetal, we're going to represent it like this. Okay, there's no sharing of electrons. It's transferring electrons, giving away electrons to form ions. Covalent, co meaning sharing, co, like if you cohabitate, that means living together. Co means sharing. Valent, valence electrons. We're sharing valence electrons, so we have to represent those as bonds. So it's this method. So nozzle method for covalent molecules. All right, so let's look at another one. Oh, first, things to keep in mind as you draw these. Electrons are negatively charged. So what does that mean? That means that negatives repel negatives. So back in our, let's see, oh, we haven't done that example yet. I'm going to show you an example of when this is going to really come into play here. Negatives repel negatives. When adding bonds or lines, you want to distribute them symmetrically around the central atom. And the honk rule, you want to try to follow the honk rule. And there are some exceptions, and we are going to see an exception to the honk rule. The honk rule is hydrogen, 1 bond. You can see it's in the first position. Oxygen, 2 bonds. It's the second letter. Nitrogen usually gets 3 bonds. It's the third letter. Carbon usually gets 4 bonds. It's the fourth letter. Okay, so again, honk. 1, 2, 3, 4. Hydrogen 1, oxygen 2, nitrogen 3, carbon 4. Okay, honk rule. So electrons are negatively charged. When adding bonds, you want to do it symmetrically, and you want to try to follow the honk rule when you can. All right, so let's look at another one. Nitrogen and chlorine. Nitrogen's a nonmetal, chlorine's a nonmetal, so we have to use the nozzle method. Okay, in needed electrons, we don't see any hydrogen here, so each one of these is going to need 8. So we have 3 chlorines. 3 times 8 is 24. And we have 8 here. 24 plus 8 is 32. So we're going to need 32 electrons if every one of these elements is going to have a full valence shell. But we know we don't, because these are not noble gases. So how many do they actually have? Well, nitrogen has 5 valence electrons. It's in group 5. Chlorine is in group 17, so it has 7 valence electrons. So 7 times 3 is 21. 21 and 5 is 26. Okay, so we're going to subtract these. So 32 minus 26, that's going to be 6. Okay, I count on my fingers just so I make sure I get the number right. There's no shame in that. Don't worry about it. If I see you counting on your fingers, it's no big deal. I don't care. All right, I'd rather you get it right. So we have 6. Now remember, on this, these sharing electrons, it takes 2 electrons when you share to make a bond. So we're going to divide this number by 2. That's going to give us 3 bonds. Okay, and I usually don't write out the whole word bonds. I usually just put a B there. So let me go ahead and do that. All right, 3 bonds. Subtract again, so 26 minus 6, that's going to leave me 20 lone electrons. Lone electrons. All right, so there's my formula. 3 bonds, 20 electrons. Let me just circle that in red. Okay, so when I draw this, this is my recipe. This is my formula. All right, so what goes in the center? Well, looking at this, we see that we have 1 nitrogen, 3 chlorine. So the one we have least of usually goes in the center. So that's going to be nitrogen. So I'm going to put nitrogen in the center. I have 3 bonds. We want to distribute these symmetrically because these bonds are electrons. Electrons push on other electrons because they're negative. So you want to get these equally spaced. So the way we equally space these is by putting them in a Y configuration. Okay, so for example, let me go back. Here we had carbon, okay, and we had 4 bonds, but we only have 2 things that are attaching to this carbon, right? So we put the oxygen on this side and on this side, and if we symmetrically distribute these, it's going to be on 180 degrees, right? Wait, no, that's, 180 degrees, okay? But since we have to evenly distribute 3 things around this, and we have 3 bonds to do that, symmetrically, that's going to make a Y configuration. Okay? All right, so what's on the end of each one of these bonds? A chlorine. So I'm going to put chlorine here. And then we have 20 electrons that we need to distribute. So we're going to start with the center. How many electrons does this nitrogen see? It sees this bond, 2, 4, 6. Well, the whole purpose in this is trying to get it so that it has 8 electrons. So we're going to need to add 2 electrons to this. So we add them in pairs. Don't add one to the right and one to the left because electrons travel in pairs. Like, see, this is a pair of electrons, but it's a bond because we have 2 elements that are sharing these. Well, no one's sharing these electrons because these are lone electrons. So we're just going to represent them as dots, but it's a pair of dots. Okay? So now we move out to the outside. Just pick one of these chlorines. Let's start with this one. This chlorine thinks it has 2. So 3, 4, 5, 6, 7, 8. This chlorine thinks it has 2, 3, 4, 5, 6, 7, 8. This chlorine has 2, 3, 4, 5, 6, 7, 8. All right, so let's go back and check. 3 bonds, 1, 2, 3, 20 electrons, 1, 2, 3, 4, 5, 6, and 6 is 12, and 6 is 18, 19, 20. That is the Lewis structure for NCl3. All right, easy peasy. See how easy that is? It's much easier than following the 10 steps that is outlined in your book. But you know what? If you want to go back, and I'm not going to teach you those steps, but if you want to go back and look at your book and learn those steps, if this is too hard for you and you want to learn those steps on your own, knock yourself out. But my experience in teaching chemistry all these years, this is the easiest method for you to learn. All right, let's do another one. Nozzle, CH4. Okay, we have carbon, and here we have hydrogen. All right, so here's this hydrogen that we have to worry about. It only needs 2 electrons each. Okay, so we have 4 of them. 4 times 2 is 8. And this carbon needs 8. So 8 and 8 is 16. So we're going to need 16 electrons if everybody is going to have a full valence shell. We know we don't. We know we do not have everyone with a full valence shell. So how many does it actually have? Carbon actually has 4 valence electrons. Each one of these hydrogens has 1, but there's 4 of them, so there's 4 there. So 4 and 4 is 8. Okay, subtract these two. 16 minus 8 is 8. We need to divide this by 2 because this tells us how many bonds we have. So we have 4 bonds. Subtract again. 8 minus 8 is 0 lone electrons. So we have 0 unshared electrons, lone electrons. So here's our formula right here. 4 bonds, 0 electrons. All right, so now let's draw that. What goes in the center? Carbon always goes in the center. Okay, we have 4 things that are attached. We have hydrogen. That looks like a G. Sorry, let me fix that. Carbon in the center. Okay, 4 hydrogens. Now distribute them evenly. So if we have 4, we know we're going to have 1 on this side, 1 on this side. Erase that dot so that doesn't confuse you. 1 on this side and 1 on this side, distributed evenly. Okay, 4 bonds, 1, 2, 3, 4. Okay, 4 bonds, 0 electrons. All right, so we need to check to make sure everyone sees the valence electrons that they want to see. So carbon here sees 2, 4, 6, 8. So carbon's happy. Hydrogen, remember, only wants to see 2 because it has that one shell. That one shell can only hold 2. So here's 2 for this hydrogen, 2 for this hydrogen, 2 for this hydrogen, and 2 for this hydrogen. Now you're going to say, but I've already counted this 2 for carbon. That's right. This is, remember, covalent, sharing valence electrons. So this carbon is sharing these 2 electrons with hydrogen. So carbon sees them and hydrogen also sees them. So we can recount those when we are counting for different elements. So this is the Lewis structure for CH4. Now, I'm going to point out something that I have been doing, and I want to assure you that it's okay if you do this. So the first time I showed you this, I put carbon, right? And I said there's 4 things attached. And so I did this, right? I put these hydrogens symmetrically around it, and then I added the 4 bonds. But on the last one I didn't do that. I did the bonds first. So I did carbon, okay? And then I need 4 bonds. So I did this. I drew the bonds in, and then I said I have 4 things to attach. 1, 2, 3, 4. You could do it either way. You could add the things that are attached first, or you could add in the bonds first. Okay, it doesn't really matter. But we're going to see in a minute where you might run into a little snag if you do it one or the other way. It doesn't matter. Okay, and I'll show you both ways. So that's CH4. Okay, so Lewis structures for polyatomic ions. I know this is dragging out, and I'm sorry because I'm doing a lot of examples. Polyatomic ions. Well, we have these things when we do ionic structures called polyatomic ions, poly meaning many, atomic referring to atoms, and it's an ion. So it's a charged like NO3, you're going to see have a negative charge. And we'll talk more about these when we start talking about bonding. But I want to show you real quick the Lewis structure for polyatomic ions. All right, so here we have NO3. You can still use this Lewis, nozzle method to draw a Lewis structure for NO3. Well, here we're going to use NH4. This is another polyatomic ion, NH4. Okay, it's called ammonium. So let's look at how we draw that. So needed. Okay, so this has hydrogen, and hydrogen only needs 2. 2 times 4 is 8. So these 4 hydrogens have a need of 8 electrons. This one needs 8. So 8 and 8 is 16. Okay, so if we're going to have all the electrons we need 16. We know we don't have those. So each one of these hydrogens only has 1, but there's 4 of them, so that's 4. This nitrogen is in group 15, so it has 5 valence electrons. So that's 5 plus 4 is 9. Well, we see here we have this charge. So we need to take into consideration that charge. And Actual is where you do that. So what does a +1 mean? +1 charge means that it gave away an electron, so it has a +1 charge. So we need to take away 1 electron from that 9 to leave us 8. So we really actually only have 8 electrons. So here, actual is where you take into consideration this charge. All right, so subtract 16 minus 8 is 8. We're going to divide that by 2 because that tells us that we have 4 bonds. Subtract again, 8 minus 8 is 0 lone electrons. Okay, so here's our recipe for this polyatomic ion. We have 4 bonds and 0 electrons. What goes in the center? We only have 1 nitrogen, 4 hydrogen. Hydrogen never goes in the center, so nitrogen is going to go in the center. Okay, we have 4 bonds, 1, 2, 3, 4. What's at the end of those? Hydrogen. Okay, and since this is a polyatomic ion, it's an ion, we had to put it in brackets. Okay, and then we had to represent the charge outside the bracket. Just like we did a single ion, like chlorine, we have to put the charge, put it in brackets and put the charge outside. All right? Polyatomic ions. All right, so here's our last, we made it to the end here. Here's our last example that I want to show you, and this is called a resonance structure, and I'll explain what that means in just a moment. But here we have CO3 minus 2. Okay, so let's start counting. Needed electrons. So we have hydrogens not here, so everybody is going to need 8. We have 3 here and 1 here, so that's 4. 4 times 8 is 32. So we're going to need 32 electrons if all of these are going to have a full octet. We know we don't, so we need to count the actual number of electrons. So oxygen is in group 16. It has 6, but there's 3 of them, so that's going to be 18. Carbon is in group 14, so it has 4 valence electrons. So 18 plus 4 is 22. But we see we have a charge here. Okay, so that's why I didn't write it here, because I saw I had a charge. So the actual number, -2, means it's gained 2 electrons. Electrons are negatively charged. So if it has a negative charge, it means it gained 2 electrons. So it has 24 actual electrons. Okay, 24 actual electrons. All right, so subtract these two. 32 minus 24 is 8. I'm going to divide that by 2. That's going to give me 4 bonds. Okay, subtract again. So 24 minus 8, that's going to be 16 electrons, lone electrons. So here's my recipe, okay, for drawing this. All right, so what goes in the center? Carbon always goes in the center. So I'm going to put carbon here. How many bonds do I have? 4. So 1, 2, 3, 4. How many things am I attaching to that? 3. Oops. Uh-oh. Wait a second. So if I have carbon in the center and I'm only attaching 3, but I have 4 bonds, it can't be this way. So here's that example I was telling you about. If you add bonds first, you might run into, if you add the lines first, you might run into this snag because only 3 things are attached. So if I'm attaching 3 things, it's in a Y shape. So I'm going to go ahead and add these. Okay, so now I'm going to add my lines. I know that each one of them at least has 1 line, but I have 4 bonds. So am I going to add it here, here, or here? Well, guess what? It doesn't matter. You're going to add them in all 3 locations. So I need to draw another shape where, let's add it here. Okay, so let's draw another one of these. And this time, let's not add it here. Let's add it here. And in this one, I'm going to draw it again. And let's not add it here or here. Let's add it here. Okay. So this is what's called a resonance structure. All three of these exist. This fourth bond travels around to the different locations at the speed of light, all the way around like this. So it resonates. Okay. This is called a resonance structure where all three of these exist, where that bond travels around at the speed of light. All right, so let's go ahead and finish this off. So we have 16 electrons. So this oxygen, well, let's start with carbon. You always start in the center. Carbon, 1, 2, 3, 4, 5, 6, 7, 8. Carbon already sees 8. So this oxygen sees 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. That was sloppy how I put those on there. It's okay. All right. So did we use 16 electrons? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And we used 4 bonds, so this is correct. So see here, this oxygen that has the double bond only gets 4 electrons, where these that have the single bond get 6 electrons. Well, let's do that over here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. All right. Same thing over here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. All right. So there we've drawn all 3 structures. Now, this has a -2 charge. Now, it doesn't matter in resonance structures. When you draw resonance structures, you're always, even if it doesn't have a charge, you're always going to put them in brackets. Okay, so if this didn't have a charge, and sometimes they don't always have a charge, I'm going to put all of these in brackets like this. So this is a lot of drawing on resonance structures, I know, but it's okay. And you're going to put an arrow in between showing that it goes from this to this, to this, to this, to this, to this, speed of light. But since this is a -2 charge, we're going to go ahead and add a -2 out here on each one of these. Okay. All right. So we're going to have some practice sheets that I'm going to give you, some practice problems. We're going to have a lot of practice on this. Just remember, nozzle means needed, actual, subtract, and loan. Okay. Nozzle. And that's it for the notes. So make sure you slap that like button right across the face. Give me a thumbs up. And if you leave a comment that's not trolling, then I'll post the comment.